All right. Good evening. I'll be doing the presentation on the hydropower for civil engineers with the module code HYP 4801. This is the assessment project for the Maguga Dam hydropower analysis, where this will be the comparison of the assessment of the storage base versus the run-off river system. Then my name is Jonathan Nzabo with my student number 56964781. Then on the executive summary, the presentation will be as follows. The overview, which will look at the performance of the dam, the hydropower dam scheme in comparison with the runoff river system downstream, and then the context, that will be number 2 on the Maguga Dam, the purpose of the dam itself, that where it supplies the domestic use, the ecological supply function, the irrigation, including the hydropower. And then lastly, the focus will be on the main findings. The main findings on the Maguga Dam, meaning the delivery, where the Maguga Dam delivers about 3.3 megawatts of power, and that will also be discussed in detail on the presentation. Then the background, the Komati Basin or the river itself, it's between two countries, that is Swaziland and South Africa. And then the dam itself was completed in 2001 and is a major multi-purpose reservoir supporting the surroundings in terms of the water supply, the irrigation, including the ecological flow and the hydro power. And then the dam itself, it plays a vital role in fulfilling the cross-border water sharing agreements between the two countries. And then the regional development strategies emphasize the integration of water and energy planning, and then the feasibility of a runoff river alternative is to explore due to its low environmental footprint. Then lastly, this study investigates whether the ROI system could match the performance of the Maguga within the constraints. The hydrological analysis, the Komati River exhibits a strong seasonal with over 70 of the annual flow occurring between December and March. And then during the dry seasons, the base flow declined below 5.04 cubic meters per second at 95%. And then the historical drought events, such as the one that occurred in 2007 and 2016, resulted in an extended low flow period that had a challenge in terms of operation the hydropower. And then the climate projection indicates that 10 to 20% reduction in the mean annual rainfall by 2025. And then now these patterns highlight the importance of upstream storage to regulate flow and provide water security. And then lastly, the seasonal flow unreliability pose a major constraint to runoff river energy generation in the region. And then in terms of the Maguga hydropower scheme, the dam characteristics, the water allocation function, the hydropower infrastructure, the energy output reliability. And then the dam itself, on the characteristics of the dam is an 8-field dam, which was commissioned in 2001, and then it holds a gross storage capacity of 332 million cubic meters, and then the surface area of the dam at a full supply level, it's at about 10.2 kilometers squares. And in terms of the allocation, as I said, the allocation is on the irrigation, the domestic use, the ecological releases, the hydropower, which will be the main focus. Then on the hydropower infrastructure, it's equipped with a multi-level intake structure to manage the temperature and water quality. And then the crosshead is approximately 110, and then uses a medium head Francis turbine with high conversion efficiency. And in terms of the output, the energy output and reliability, and then it delivers roughly about 3.34 megawatt firm power. And then the storage enables a drought resilience and consistent generation during the dry seasons. Then in terms of the runoff river alternatives, the site allocation, the technical characteristics, the hydrological constraints, and the energy output. If we look at the site layout, it's a proposed site located approximately 2 kilometers down the stream, and then no large reservoirs. And then the layout indicates an intake where the canal, the petstock, and the powerhouse. And if you look at the technical characteristics, an estimated gross head of about 20 meters is based on the elevation drop, and then the turbine options is limited to low head designs such as the Kaplan or the crossflow. Then now it requires a long conveyance structure to increase the hydraulic losses. And then on the hydrological constraints, firms discharge an estimated of 5.04 cubic meters per second at 95%. And inadequate flow during the dry season reduces the firm power to 0.84 megawatts. And then the high sensitivity to seasonal and daily flow fluctuations. Then in terms of the energy output, the annual generation estimated at 7.4 gigawatts per hour. And then the low capacity factor compared to storage. And lastly, it's on the frequent outage expected during the flow period. And then this slide is the runoff hydropower plant, a typical layout of the hydropower plant with the intake, the conveyance canal, the penstock there, and then this is the powerhouse where electricity is produced. And then the structural and the mechanical assessment, the Maguga dam infrastructure, it's a gated spillway with a radial crest gate for flood control. And then it has the multi-level intake tower for water quality management. And then the silting basin to dissipate energy and prevent downstream erosion. That is the infrastructure of the dam. The electromechanical components, it comprises of the Francis turbine for medium head, and the efficiency of just over 90% under design, and the short penstock reduces friction losses and improve performance. In terms of the modernization needs, the H turbine and control system requires an upgrade, and then the efficiency losses due to cavitation, sediment, abrasion of and wear. And lastly, on the recommendations, the variable speed turbine to handle variable head conditions. In terms of the flow duration curve, that is your FDC. These are the following. The hydrological pattern is looked at, the key flow duration curve observations, implications for the designs, If you look at the hydrological patterns, it's highly seasonal flow regime typical of a semi-arid basin. That is over 70% of the annual flow is concentrated in 4 wet season months, and then the dry season flow fall to 5.0 cubic meters per second at 95. And then the key FDC's observation that the steep upper curve, it has a high flood peak. Peaks are short-lived, and then the flattened lower curves, low base flow dominates dry season, and the firm flow of the ROR is equals to only 5.04 cubic meters per second. Then on the implications of the designs, the Maguga storage buffers low flow is a consistent turbine operations. And then the ROR plant would face frequent shutdowns in dry months. And then lastly, the highlights the operation and unreliability of the ROR under regional flow conditions. And then the hydraulic head calculations, these are some of the calculations that are used in the ROR system. The Google Earth Pro is used, and then with the gross head system estimated at roughly about 20 meters flow, and then the flow conveys through the long canals and pipe increase energy losses. And then the formula for Darcy on the friction losses. This is the formula, the friction loss formula with the length, the diameter, the velocity, the friction factor. And then on the net head estimate, the net head estimate equals to the cross head minus the friction losses minus minor losses. And then on the lower net, reduce turbine efficiency and availability power output. And then the Maguga dam advantages, the short penstock and high gross head at Maguga keeps low head losses just below 3. And it also enables a consistent turbine performance and minimum hydraulic efficiency. Mm. And then if you look at the topographic and storage analysis, this is the analysis that I've done. The GIS and the terrain mapping, as I said, the QGIS was used, the digital elevation model, and the KML shape files processed in the QGIS. And then just extracted elevation contours and also the key elevation, the full supply level, which is equals to 625 meters, and inactive level is equals to 550 meters. On the reservoir geometry, the elevation is minus the area minus the volume curve is derived from the contours analysis. And then the reservoir surface area on the full supply level is equals to 10.2 kilometer squares. And then the gross storage capacity, as I said, is just over or equals to 332 million cubic meters. The drawdown and the head calculations, drawdown head calculations equals to the full supply level minus the IL equals to 75, and then on the gross head for power generation, which is equals to FSL minus tail water elevation, which is about 110 meters. And then still on that, the support stable turbine operation even with seasonal water level variations. And then if you look at the operational benefits, the large storage volume allows seasonal flow regulation. And then the buffering capability ensures consistent water release for power, irrigation, and other uses. And then it also provides draft resilience unmatched by ROR system. Then this slide is the topographical map. The dam itself, it's allocated there on the red part. And then these are some of the graph and the calculations that were done. The surface area, the cumulative storage, roughly there. And then the mass balance, reservoir modeling, the following on the model. I looked at the storage dynamics, the water allocation, the operational scenarios. And then the storage dynamics, the reservoir behavior model using water balance equation. This is the equation with all the variables. And then on the water allocations, as I've indicated that there's a number of supply from this dam, that is domestic use, environmental flow, energy generation, and also irrigation. And then on the operational is that there's a 30-year inflow data used to simulate monthly storage level. Scenario tested at 2%, 5%, and 10% failure probabilities. Then on the energy output and the turbine sizing, this is the equation, the hydropower equation. There it is with the P for power and then N for efficiency. And then this will be the density, G for gravity, 9.81, and Q for the flow rate, and H for the net head. And then the Maguga system performance, firm discharge supported year round to the reservoir storage, and the net head of 110, and the design flow enables the firm power of 3.34 megawatts, and then which is the annual generation of 29.3 gigawatts. Then if we look at the run-off river output, the net head limited to 17 to 18 meters due to friction and the topography. And then, as I said, the firm discharge of 5.04 cubic meters per second yield. And then with the annual generation of 7.4 gigawatts with a lower capacity factor. And then if you look at the efficiency considerations, Maguga higher head and stable flow support turbine efficiency of just over 70%. 90%. Then the ROI turbine efficiency reduced by variability and head losses. And the storage-based design ensure better reliability energy return per unit. Then now, if you look at the comparative performance summary, just in summary, one, the firm power and energy yield, Maguga, it's supplying 3.34 megawatt, and then that is equates to the power of 29.3 gigawatts per year. And then with the ROI of 0.84 megawatts at 7.4 kilowatt per year. And then the Maguga provide over the energy output due to its regulated storage. Then if you look at the head losses and the hydraulic efficiency, and then the head loss, it's just under 3% due to short penstock and high head losses. And then the ROI is 10%, over 10% on the head losses from the long canals. And then the reduced net limit turbine performance. And then on the drought resilience, the storage system buffers seasonal variability. ROI generate fails during dry season when it flows. And then Maguga maintains operation during low inflow years. And then on the multi-purpose value, the Maguga support irrigation, domestic use, hydropower, and also ecological flow. And in terms of the ROR, is limited to electricity generation with a little operation flexibility. And then if you look at the storage-based system, enables integrated basin-wide water resource planning. And now if you look at the recommendations, it's 4 of these recommendations: infrastructure modernization, adaptive management tools, hybrid energy integration, and environmental flow. On the infrastructure modernization, there is the upgrade turbine and penstock to reduce variable head. The target of 10% improvement efficiency within 2 years. Introduce the automatic debris screens and variable speed turbines. On the adaptive management tools, develop a probabilistic reservoir model within 3 years or 36 months. Integrate seasonal forecast and real-time monitoring. Apply dynamic rule curve for drought resilience. Hybrid energy integration, that is the third recommendation. Install a floating solar PV, that is a target of 5 megawatts. Reduce evaporation at least by 8 to 10%. Explore ROR plus solar cluster to capture excessive wet season flows. Then on the environmental protocol, design adaptive ecological release, implement which should be implemented by within 2 years by all the stakeholders that involved, and then ensure at least 95 reliability even during dry seasons. Then in terms of the conclusion, first conclusion is that Maguga Dam delivers a significant higher firm power of 3.34 megawatt than the proposed runoff river scheme of 0.84. Then if you look at the generation, it generates over 4 times more annual energy compared to the ROI options. And then it maintains a stable performance during drought or tough seasons. It also supports multi-use of water, like the irrigation, domestic use, production of energy, ecological flow. And then on the runoff river system, it's highly sensitive to low flow and not suitable for baseload power generation. And the strategic improvement should include infrastructure upgrade and reservoir modeling. And then lastly, the hybrid integration with solar UPV can enhance drought and resilience and reduce evaporation losses. Then in terms of the references, these are some of the references that I've used to do this analysis. Ladies and gentlemen, thanks very much. This is the presentation for the hydropower project presented by myself, Jonathan Thabo. Thank you.